In the first step of the computer science, knowing the fundamental concept is essential. Because when you want to write a program, your goal should be to write a good program. To write a good program, there are some prerequisites that we need to know. If we don't know them, the program we write usually won't be a good one. Our intention in this series is to review these prerequisites together. My name is Amir Azarbashi, and here is Thinking CS. In the field of computer science, we have three types of work. A major part of the work usually consists of theoretical work. This part includes research and studies that focus on the fundamentals and basic questions in the computer science. For example, questions such as whether it is possible to build a computer that can solve all of our problems or not. Then, part of the knowledge produced in the field of theoretical computer science is used in computer engineering to build tools that are applied in practice. And then some of tools that are built are used in practice and have various applications, which are what we see today in computers and their applications. Now, let us examine theoretical computer science in a bit more details. In the theory section, we can ask many different questions. For example, we can ask, what does computation mean? This is a very fundamental question. To answer it, we need to go back to year 1932, when the most important figure who essentially formalized the concept of computation and proposed a theoretical model for it was Alan Turing. The machine he introduced was called the Turing machine. Now, what is a Turing machine? The answer is that a Turing machine is a mathematical model of modern computers. In a Turing machine, we have a tape on which a set of symbols can be written. And this tape is infinite in both directions. We also have a head that can read one cell of the tape at a time. In addition, there is a state machine that can move between a finite number of states. Computation then means, at the current moment, what symbol is the head reading on the tape, and what is the current state of the machine. Based on the symbol and the state, the machine can change its state, replace the symbol, and move the head one cell forward or one cell backward. This model can be expressed in a precise mathematical form. After Turing machine was introduced, other questions were raised. For example, whether these machines can solve all of our problems or not. At this point, a branch called computability theory emerged. The goal of the branch is classify which problems are solvable by Turing machines and which problems are not. The first problem that was proven to be unsolvable was the halting problem. The halting problem is formulated as follows. If I am given a description of Turing machine and its input, can I determine whether this Turing machine will eventually halt after a finite number of steps or not? It was ultimately proven that this problem is undecidable. Finally, once it became clear that some problems are solvable and others are not, it was also recognized that for solvable problems there may be more than one solution. At that point, we need to choose which solution is more suitable. This led to emergence of a field called computational complexity. This field focuses on problems that are solvable, and its goal is to analyze how complex these problems are. It was found that some problems can be solved very quickly, while others cannot. Eventually, classifications began, and one of the most well-known classes is P, which includes all problems that are easy to solve. Easy means that I can use computer to solve them. On the other hand, the class of problems NP emerged, meaning that if we have a machine that works non-deterministically, some problems can be solved efficiently. However, a class of problem was eventually identified such that even if we use a non-deterministic machine, it still takes a very long time to obtain a solution, making them impractical in real applications. This class of the problems is called NP-hard. Now, when we talk about determinism and non-determinisms, if we consider a Turing machine, suppose we are in a specific configuration in Turing machine, for example, the symbol A is under the head on the tape and the current state is Q. If the next move is uniquely determined, this is the determinism. But if the next move is not uniquely determined, or the machine can take multiple possible moves at the same times, this is the called non-determinism. And one of the questions raised here is whether the class P is equal to the class NP or not. We still don't know the answer, and it remains an open problem with a $1 million prize. Then for problems that fall into the class P, the question arises as to which algorithms can be proposed for solving them. And if the multiple algorithms exist for the single problem, which one is better? Therefore, we need criteria to determine what makes one algorithm better or worse, which lead to the study of algorithms and their complexity. After that, the question of how data can be stored arises, and if there are specific relationships among the data, fields such as graph theory emerge. Additionally, we consider how to design algorithms that solve problems related to computational geometry and so on. The final point regarding theoretical computer science is that when we work in this field, mathematics has a special importance. For this reason, in the most universities around the world, the computer science department and the mathematics departments are located next to each other or work closely together. This was a summary of the discussion on the theoretical computer science. In the next section, we will examine how the knowledge developed here can be applied in the computer engineering.